Hello, my name is Matt, and I've been talking about the Attiny85 in the last couple of videos. During those videos, I showed how to make a little voltage meter using only the Attiny85 and an OLED and no extra parts. So let's just demonstrate that here. Plug it in, and you can see it is telling me the voltage of this battery. So what this video is about is how this works. In this segment, I'm going to talk about how we hook up the hardware to the chip. So for that, I'm going to use a program called Voltmeter, which is a free program that you can use to simulate circuits. It's definitely worth checking out. We'll start with a blank circuit, and I'm going to start by making the ADC that is built into the chip. So you don't have to build this, it's already inside the Attiny85, but I'm just putting it here so that we have a visual aid so that we can see what's going on. So this is a 4-bit ADC. The one in the Attiny85 is 10 bits. It's got a 8 and 10-bit mode, but we're going to use the 10-bit mode. The other part we're going to add for our own visibility is a decimal display. So this will convert these binary bits into a number that we can look at. So we'll use 10 bits, move this over here and hook it up. So like I said, this is all built into the chip, and our code is just going to have to deal with this number. So we'll provide this, and then our code will get this number and it will have to deal with it. So let's start with the traditional case. Actually, let's just start by messing with it. We'll start with a voltage of 5 volts, and then we'll put another voltage up here, and you can see we're maxed out at 1023, which is all these bits are high. So to make it more interesting, we'll change it from 5 to 0. So now I have a little slider here. I can change this voltage, and you can see as the voltage goes up and down, the number goes up and down. So 0 volts is 0, 5 volts is 1023, about halfway is about halfway. So our code would read in this number here, and it would have to use math, knowing already what this number is, to determine what this number is. So I'm going to start by talking about how these things are traditionally built and how you'd usually want to build it, and then we'll get into the case that only has 2 parts. So traditionally, you're going to start with a voltage source. So we're going to say in this case that we're feeding the chip 5 volts, just to make the math a little bit easier. Of course, you could also feed it 3 volts or 3.3 or whatever. And here we'll say that we're going to use a LiPo battery with 4 cells. So LiPo batteries have 4.2 per cell maximum. So if there's 4 cells, it'll be 4.2 times 4, which is 16.8. And then LiPo batteries, you usually don't want to take them under 3 volts. So I'll just say the minimum here is going to be 3 times 4, which is 12. So that'll be our range for our battery. So we move this around and we can see us moving in between those ranges. So if we hook this directly here, there's of course a problem that on the simulation we get 1023 all the time. In real life, you would fry your chip and have to get another one. So we can't do that. So what we do is we have to divide that down. And the simplest way to do it is using a resistor divider. So just 2 resistors and ground. And then the size of these will determine how much current is going through. But of course, the chip itself has a specification for how big you can make them. You can't make them too big or this will fail to function. So here we divided the voltage by 2 because we made these equal. So we would have 8.4, which is still too high, but we'll hook it up anyway. So let's put our test point there so we can see where we're at, 8.4. We'll wire it in. So we're still at 1023, and then we can lower this resistor here to make it reasonable. So let's say 3K, now we dropped it to 6.3, still too high. 2.2K, getting close, but still a bit high. So we'll say 2K. Okay, a little bit low, but in real examples, you'd probably just accept this because 2K resistors are easy to come by and it's close. So here we're at 982 when we're at the full 16.8. And as it drops, we go down to 701. So that's our range, 701 to 982. And I'm only scratching the surface of design here. For example, you could put a filtering cap in here to trade off between readout speed and stability. You can mess around with these resistor values. You can use op amps to either scale up the voltage for weak voltage sources or buffer it for really weak voltage sources, or to shift it if you want to use more of this range. A lot of chips like the Attiny85 have an analog reference pin that you can use to give it a cleaner voltage. And there's also considerations on how you want to route your analog wires to keep the noise down. So that's all topics that could be looked into that we're not going to cover here, because here we're going to keep it simple. Now we're going to use the case where we don't need these resistors. So out of the gate, you can only do voltages that you can feed directly to the chip. 1S LiPo is a good example. So for a 1S LiPo, it's the same thing as our 4S LiPo, except there's only one cell. So we change this, maximum value 4.2, minimum value around 3. Now for this case, we're feeding this directly into the Attiny85, so there's no voltage regulator or anything like that. And the Attiny85 can run that way, so as long as we keep the voltage between 1.8 and 5.5, we're good. But of course, we'll need a little bit more in order to drive the OLED. But we'll start off at 4.2. And then for the Attiny85, you can actually select an internal bandgap reference for the input. In the code, you say, hey, Attiny85, I want to use the bandgap reference. And when you do that, it internally hooks up a 1.1-ish voltage source to the input, like that. This is basically it. So now, when you're at full 4.2, you'll read at 267. And as we go down, the the number here actually goes up. And it goes all the way up to 375. So you can see we're not using a huge amount of our range here, but we saved on 2 parts. And it might be good enough. So in the next section, we're going to talk about the math that's needed to get from this number here to whatever our voltage is down here. Okay, so now we're going to do a little bit of math so we can learn how to figure out the voltage based on the ADC value. So if you're not into math, feel free to skip to the next section where we just look at the code. So we'll start by saying this is an Attiny85, and we're going to give it a Vin value. And inside the chip is the A that we measure, and a VB, which is the fixed bandgap voltage, which is around 1.1 volt. So the equation relating the 3 is VB times 10 times 1023 divided by Vin equals A. So I tried plugging this into actual code and running it, and I found that I didn't get very good results. No matter what I set VB to, it was always off in one end or the other. So I was actually able to make it better by adding in another term here, VD, which is a voltage drop. So the theory there is there's a little bit of drop between here and where it's actually measured inside the chip. And when I did that, I was able to get good results. But I found that you have to calibrate it for the specific chip that you have and the way you have the circuit set up. So the rest of this, we're going to look at how to do that. So to start, we'll just solve for VB real quick. So we can multiply both sides by this Vn minus Vd and divide both sides by 1023. And we end up with VB equals A. Vn minus Vd divided by 1023. And what we'll do now, so we need to find this VB value, and we need to find this VD value. So that's the real band gap voltage for the chip and the voltage drop. So in order to do that, we are going to control Vin and measure A. So we'll do a 3-volt case and a 4-volt case. And at this point, I'm just going to switch to millivolts, because then I can use integer math in the code. So we'll write VB equals A at 3 volts. And we'll say 3,000 millivolts. We're going to actually set that to that, minus VD divided by 1023. And then the other case, VB equals A4, 4,000 minus VD divided by 1023. So these are our two experiments again. We set the voltage to 3 volts, measure A3, set the voltage to A4 volts, measure A4. Okay? Now we want to subtract that equation from that equation so that we can solve for VD. So let's do that. So we'll subtract the top from the bottom. So VB minus VB is 0, and this will just write out. And then we'll continue to do some algebra so that we can simplify this. Okay, so both terms have a denominator that are the same, so we can combine them like that. And then the other thing we can do is we can multiply both left and right by this 1023. So 0 times 1023 is still 0. And this side times 1023, that just disappears. Okay, now we'll multiply it out. Actually, we'll put the 3,000 in front. 3,000 A3 minus VD A3 minus 4,000 A4 plus, because of the double minus, VD A4. Now we'll move all the VDs to the left side. So VD A3 minus VD A4 equals 3,000 A3 minus 4,000 A4. Okay, and then we can combine this, so we can say VD A3 minus A4. So I'm just combining that, equals this same thing. And then we'll just divide both sides by this A3 minus A4. And we end up with VD equals 3,000 A3 minus 4,000 A4 divided by A3 minus A4. So now we have a way of taking our two ADC measurements and finding VD. And then we can plug that into either one of these equations to find out VB. And then we'll have VB and VD, so we can solve this equation. So we'll just do that real quick to get the final one. So we'll multiply both sides by Vn minus Vd. So we have VB times 1023 equals A times Vn minus Vd. And we need to solve for Vn, so that equals A times Vn minus A times Vd. We can move that over there. So we can say VB times 1023 minus, or plus I should say, A times Vd equals A times Vn. And then we can move that over there. So let's just do that real quick. So we'll just divide both sides by A. So we say Vn equals VB times 1023 divided by A plus VD. All right, so the equations that we're going to use in our code are this one, and either of these two. I'll just pick this one. And with these three equations and a couple of measurements, we'll be able to implement the code. So, sorry if that was too complicated, but as I will show, when I put it in the code, it will do what it's supposed to. Okay, so now we're just going to talk a little bit about the code. So first I'll point you to the Attiny85 datasheet, which you can find just with a Google search. But there's a whole section in here on the analog to digital converter, including how it's set up and different ways that you can configure it and what the different registers are. I'm not going to go through all of that because I feel like we'd get too much off track if I do that. So here I have my project AVR Pico, which I'll share the link down in the description, and you can use that to get to the code that I'm using here. So this is a library called ADC. This is the simple version, which is just manipulating the two registers. So you got the 80 mux to decide your input and your reference, and then you're setting it up, and then you're waiting for it to finish the sample. And this is the actual code that I'm using to call it. So most of this stuff in here is just fonts. So in my last video, I talk about how to work with these fonts and the OLED and things like that. So I'm not going to cover that again here, but feel free to check that video out if you want details on how this part works. All of the code I decided to put in one file for this project called main. So if we go there, I always like to put a little diagram of the chip at the top. So here you can see we have the chip, and then you have SCL and SDA to talk to the OLED. And then there's this Cal pin that you can pull to ground. When you're using the chip in its final form, this can be left floating, not connected to anything, but you have to go through this one-time procedure to tell the chip where 3 volts are and where 4 volts are, so that we can calibrate what the band gap and offsets are, just like we talked about in the last section, and as I will demonstrate in the next section. And then going down, here we're just defining the pins, save state. So here's our voltage difference and our band gap that I've been talking about. These are going to be saved in EEPROM on the chip so that they can be permanently remembered. And then here, there's an eye catcher here. This is just so that it knows if it's ever been programmed before. If I was gonna ship 1 million of these things, I'd probably also put a checksum in here because there's a small chance there could be some bit flips. But for this project, I didn't bother with that, just to keep the code simpler. This part, so this is where this structure here exists in EEPROM, and here's where it exists in our RAM. And we just copy back and forth between those. This is the implementation of a digital low-pass filter. You could use a capacitor and resistor to do an analog low-pass filter, but I'm trying to minimize parts here, so I'm doing it digitally instead. So all this is it is a ring buffer of samples, and it adds all those up and then divides by the number of samples, and it does that in a sliding window. These 3 things are the formulas that we came up with in the last section. So here we're coming up with our voltage drop, and then here we come up with the band gap, and for that we need the voltage drop and we need the 3 volts. Again, I could have done it with the 4 volt one as well to get the same answer. So these are only called when you're setting the EEPROM stuff. So it's a one-time thing. And then this is called the rest of the time. And this again is the formula that we derived in the last section, where we convert an ADC value into our final voltage in millivolts. This is just a quick function to tell if the calibrate pin is grounded, just to make the code a little more readable. These functions will read and write to the EEPROM. So this read ADC sample calls the library code and then does the averaging for the digital low pass filter. This is the second pass of the digital low pass filter, where it's just dividing the sum by the number of samples. This is OLED stuff, so this is during calibration. It just shows calibration values, as you'll see in the next section. And this shows all the calibration values. So we show the 3 volt and 4 volt raw values. And then for the next section, after it's been programmed, we show the band gap, voltage, the voltage drop, and the current voltage. And this is the calibrate code that works through all that. Normally, all this code is not called. It's only called when you first are programming the chip. The rest of the time it is not there. The init is just setting the direction for the pins and setting everything as an input, setting pull-ups, and then setting up the SDA and SCL as outputs for the OLED. Here we're doing some other initialization of structures and initializing the OLED. And here we're reading the EEPROM, and if it doesn't work out, like we don't see the eye catcher, then we set everything to 0 and we call calibration. This is what is used when we are calibrated. It's just printing the voltage in a larger font. This is a message when you plug in and you're not calibrated to you need to calibrate, and we're at the bottom. So this loop is just called in a loop. So it's checking if calibrate is grounded. If so, calibrate. Otherwise, it prints the voltage to the OLED. And this is the main. If it's not calibrated, print the calibrate message. Otherwise, just run in a loop. So that's it with how the code is written. Now we'll just go in the lab and actually run the code. So here I have my basic setup where I'm going to calibrate it, and I'm also going to demonstrate it. So the actual parts of the circuit are the Attiny85 and the OLED. And then I have a multimeter for measuring 3 volts and 4 volts to take ADC measurements. And then this is a power supply just to provide the voltage. Okay, so I reframed the shot so I could get everything as close as possible. So we have our multimeter measuring voltage and then the OLED. So I'll go ahead and apply power. And what it's telling me right now is that it's not calibrated. There's no calibration settings saved to the EEPROM. So what it wants me to do first is set the voltage, which is currently almost at 5, to 3 volts, and then ground this pin. So I'll go ahead and do that until we get near 3. It's a demonstration, so I'm going to prioritize speed over perfection. Okay, that's pretty close. So I will go ahead and ground the pin. Now the way this is set up, you can either tap ground it or you can keep it grounded. It'll work either way. Now that we got our 3 volt reading, we'll go ahead and move it up to 4 volts and get another one. So let's do that. Okay, probably close enough. So that's saying the ADC reads at 383 at 3 volts and 280 at 4 volts. So I'll just remove this to block that in. And then it's saying that our band gap voltage is a little over 1 volt and our offset VD is about 0.28 volts. So now I'll shut this off. Now that it's calibrated, it's going to bring up a different UI when I power it back up. So now we get the final UI, which shows us the voltage here. So I can move the voltage up and down here. So let's go to 4 volts, for example. And you can see, again, it's tracking pretty close. Not perfect, but close. And then we can go back down to 3 volts. There's 3 volts. And then we can take it down. We'll see how far down we can take it before it can't power the OLED anymore. So here's 2.5. This is lower than you probably want to go, but we're just going to push the boundaries here. I can see the OLED's getting dim. And it can barely hold it now, but it's still running. And then we can bring it back up. Oh, it actually locked up there. I guess I brought it down a little too low. So we'll just reset it. And then we're back to normal. So yeah, that's basically the way that this thing works. If you have questions, feel free to ask. If you have suggestions, feel free to suggest. And yeah, that's it. Feel free to like or subscribe and whatnot, and I will see you in the future. Goodbye.